All right, welcome back, ladies and gentlemen. 6.2, Antidifferentiation by Substitution. So we're going to be looking at a lot of integrals today, looking at a lot of antiderivatives, and we're going to be focusing on this idea of the indefinite integral. All right, so let's define the indefinite integral. The indefinite integral is the family of all antiderivatives of a function f of x. It's denoted as such. Notice for our integral sign, there are no index numbers. There's no indices. So we're not finding a numerical answer. And that's actually what I want to note here is when we looked at the definite integral, that's where we had numbers on the bottom and top of this. When we looked at the definite integral, the answer was a number. And that was because it was the area and it was a limit of Riemann sums. So the limit of a bunch of broken up rectangles, basically. However, the indefinite integral, is a family of functions that have a common derivative. We'll look at one here in just a second. All right, so with numbers here, that means it's an area and you're going to get a number. Without numbers, that means you're going to get an antiderivative, an actual function. All right, so let's look at an example, something we've kind of become familiar with already. If I was to take the antiderivative of this or evaluate this integral, this indefinite integral, I would look to see, well, what derivative, whose derivative is x squared? Well, I know the derivative of x to the third is x squared. But not quite. It would actually be 3x squared. So I would have to divide by 3 so I could cancel the 3's and make x squared. Likewise, I would look at negative sine of x. Whose derivative is negative sine of x? Well, I know cosine of x has a derivative of negative sine of x. And then, as always, we add our c because that's a constant that represents the whole family of functions. And remember, the only way we can find this c is if we're given an initial value. So this would be our answer, and it's easily checked. All we would have to do is find the derivative of this new function. The derivative of x cubed over 3 is x squared. The derivative of cosine is negative sine. And that means we've got the right answer. The derivative of a constant is just 0. All right, so what we need to remember is each of the derivatives that we've learned so far in this class have their equal in the antiderivatives as well. So we knew the derivative of cosine was negative sine, so we should know that the antiderivative of negative sine is cosine. All right, so things like that. So all of our trig derivatives, all of our inverse trig derivatives, all of our exponentials, logarithmic, all that sort of extra stuff is on page 332. And I want you to make a note of this, copy it down. I may or may not give you guys a cheat sheet for all of these. We'll see about that. But on page 332, it gives you a list of a couple properties, and we used one of them. We knew that with derivative rules, that if we took the derivative of the first plus the derivative of the second, we would get the answer. So we could actually take the antiderivative in that form as well. We could take the antiderivative of the first and then the antiderivative of the second. All right, and then there's a lot of trig formulas. The exponentials and logarithmics are there as well. So have those handy when you come to class, because some of you guys aren't going to have this memorized. That's just the way it's going to be. Hopefully by May 5th you will. All right, so let's look at a slightly different type of problem, and it's paying attention to the differential. What are we taking the derivative with respect to? So I'm going to give you two things. I'm going to give you f of x, where f of x is x cubed plus 1, and I'm going to let u equal to x squared. And we're going to find three things. And we're going to show how they're different. We're going to look to see that they're different. So first, we're going to find the derivative of f of x, or sorry, not the derivative, the antiderivative, the integral of f of x. So for a here, first one, I want to find the antiderivative of x cubed plus 1 dx. Well, that's pretty easy because the derivative of, the antiderivative of x to the third is x to the fourth, but in order to compensate, that has to be over 4, plus the antiderivative of 1 is x, because the derivative of x is 1, plus c. So that one's pretty easy. Let's do the same thing for the next one, f of u du. So f of u. So f of u is just going to be u cubed plus 1. Now I can't plug in what u is because the differential is du, so I actually want to take the derivative with the antiderivative with respect to u in this case. So the antiderivative here is going to be the same as before, only with u's instead of x's. Oops. Delete that. Come back here. And we'll go plus u plus c. But the part up here says I want my answer in terms of x. So now I'm going to substitute what u was. So u was x squared. So x squared to the 4th is going to be x to the 8th over 4 plus x squared plus c. Now I really want to focus on how this is going to be different than the next one we're going to do here. The antiderivative of f of u dx. So yeah, I might want to start with u cubed plus 1 dx, but the problem is now I can't find the antiderivative of this because I have two different variables. But I know that u is x squared, so now I have to change this to my x's. So u cubed becomes x to the 6th plus 1 dx. And now I can find the antiderivative. The antiderivative of x to the 6th is x to the 7th over 7 plus x, oops, darn it, plus c. So you notice how these are very, very different. Just finding the antiderivative of f of x, pretty straightforward. But really, this and this are what's super important. F of u du just says, hey, find the antiderivative with respect to u, and then substitute in for x. But the last one here says, find the antiderivative with respect to u, given a different u function, given a different u, so substituting in x to the 2nd. All right, so really notice, pay attention how different these are. They're not hard, but you just gotta have to pay attention. This is why I said pay attention to the differential. What are we taking the derivative with respect to? All right, so that's kind of gonna lead us into the, let's see here, using substitution. And so far, the antiderivatives that we've been dealing with have been very easy. Some of you might not have been thinking that, but they've actually been very easy, like the ones we were just doing. However, some of them don't look very pretty, and they don't come to you very quickly. So we have to use some sort of substitution so we can make the antiderivative easier. So what we're going to do is we're going to change f of x dx into g of u du. So we're going to be changing the function. We're going to be finding a function u, basically so we can do compositions and stuff like that. All right, so let's look to see what this looks like. Now, if you're looking at this function, you go, hey, I have no idea whose derivative is this. And that's probably a good thing, because if you did, you'd be on top of things already. But here's what I want to do. I want to say, well, let u equal something, and then I want to know what du is. Well, I know, and this is where you guys have to start just becoming comfortable with this. I know the antiderivative of e to something. So it would be really nice if this was just e to the x or e to the u. So let's take that thing that's in the exponent. So let's say u is cosine of x. Well, du is negative sine of x. That's very easy. Sine of x dx, actually. That's very, very simple. And what I want you to notice here is I have, if I rearrange this a little bit, I have a sine of x dx. But I don't have a negative sine of x dx. So I'm going to change this a little bit. And I hope everybody's comfortable with this. I just said I had a negative, and negative is going to make it positive. So I didn't change anything. But now I have a negative sine x dx. Well, negative sine x dx is the same thing as d of u, or du. So I'm going to change this to negative integral of, well, if I said cosine of x is u, I can say this is e to the u du, because negative sine x dx is du. Well, now this is super, super simple. I can say it's negative. The antiderivative of e to the u is e to the u plus c. Well, my answer cannot just remain e to the u. I need to use that u now. And u was cosine of x. So my actual answer is negative e to the cosine of x plus c. And guess what? That's it. Now, the antiderivative stuff's not the hard stuff. The green here in green is not hard. It's figuring out what should be your u function and being able to know that the du is in your integral somewhere. So this is going to take practice. This one takes a lot of practice. We'll probably spend a couple days on this one. And the next one also, by parts is what it's called. All right, so let's look at another example. Some of you guys are going to get really quick at this because you can visualize the math. You can visualize the derivatives a lot faster than others. So if you're one of those people that can't quite see it yet, you'll get there. All right, so here I'm going to say I need to know what's u and what is du. Well, I usually, it's kind of hard to say. I usually like to look at things, well, I know square roots. Square roots are pretty simple. So let's kind of think about a square root here. So let's look underneath the square root. Let's let u, and I know obviously that the derivative of x cubed is x squared. So let's start with u is 5 plus 2x cubed. Well, that means du is 6x squared dx. Well, I don't have a 6x squared. But I do have 1/6 of 6x squared. So I have a 1/6 of 6. And notice how I just said, oh, I have a 1/6 and a 6. Those cancel out to 1. So I didn't change the problem at all. And now it becomes something that I can use substitution on. So this is going to be, let's change colors here as I've been doing. This is going to be 1/6 of the integral u to the 1/2. Everybody, I'm 5 plus 2x cubed is u. The square root of u looks a lot better as u to the 1/2. And 6x squared dx is my du. Well, I can find the antiderivative of this. This is just 1/6. I know in order to find the antiderivative of things to an exponent, I'm going to take that exponent and add 1. So this becomes 3/2. But I have to cancel out the 3/2 by multiplying by 2/3, because if I take down the 3/2, that cancels. And then I get plus c, and I have to go straight to my answer now, where u was actually 5 plus 2x cubed. So 1/6 times 2/3 is actually 1/9 times 5 plus 2x cubed to the 3/2 plus c. And if you could go straight from the first question to this answer in green in one step, more power to you. I have no idea how you did it, but this is kind of how it has to go. All right. So again, I'm just looking for a function whose derivative is some other part of my integral. So I have to delete some of this. Try a different question. Cotangent of 7x dx. Now, this is where things start getting a little bit more challenging because we're not all familiar with our trig functions and their derivatives and their antiderivatives and all that sort of stuff. But I know cotangent is not the derivative of any function. So what I want to do before this, and this is just something you got to get the hang of, is I'm going to change this. Cotangent is actually cosine over sine. And by doing that, I can now look at a u and a du. Now, because there's no negatives and stuff like that, I'm going to look at this. I'm going to say u is actually sine of 7x, and du would be 7 cosine of 7x dx. Well, with that being said, I don't have 7 of them up here, so I'm going to say I have 1/7 of 7 cosine 7x over sine 7x dx. Forgot my integral sign. Well, now I have enough information that I can use my substitution. 1/7 of, well, 7 cosine 7x dx is my du. Sine x is my u. So I get basically the integral of 1 over u. And some of you guys are not quite there yet. You forget what the antiderivative of 1 over u is. But the derivative of the natural log is 1 over 1 over the variable. So I get 1 over 7 of the natural log of u. And you do have to use absolute value because u could be positive or negative. And it has to be only positive in our natural log. And now I get to substitute my u back into this, and I say 1/7 of the natural log of the absolute value of sine of 7x plus c. And now I haven't really mentioned anything here, but you can always find the derivative of what you found to verify that you got the right initial question, or right antiderivative. Right? So if you found the derivative of this thing in the box, you would eventually get cotangent of 7x. All right. Every once in a while, trig identities will show up. So this is one reason we kind of stressed it last year. So let's look at these one at a time. And I have cosine squared 2x. Well, I can't do anything with something over cosine squared because I don't have any, I can't set up a u and a du and all that sort of stuff. So I know that something over cosine squared is actually secant squared. And I know the derivative of tangent is secant squared. So, but the thing is I have a 2x in here. So I still have to use substitution. So let's go ahead and say that u is just the thing inside secant squared because secant squared has an antiderivative, which means du is 2. So in order to compensate, I need to say it's actually 1/2 of 2. Oops, sorry. Du is 2 dx. So I have 2 secant squared of 2x dx. And now I can substitute 1/2 with the integral of secant squared u du, because 2 dx was my du. And the answer here is going to be 1/2 tangent of u, and I'm going to save space here. The tangent of u would be the tangent of 2x. Oops, no d. Plus c. All right, well, what about cotangent squared? Cotangent squared, again, I don't have an antiderivative for cotangent squared. But I do have something with cosecant, so it might be helpful to use a Pythagorean identity here. Cotangent squared of 3x is going to be cosecant squared of 3x minus 1 dx. And here I'm going to say u is equal to 3x. So du is equal to 3 dx. I know something about cosecant squared minus 1, but I don't know anything about cosecant squared 3x minus 1. So that I'm going to substitute. I'm going to say it's 1/3 of 3 cosecant squared 3x minus 1. Now I can use my substitution. 3 dx is du. And cosecant, this is going to be cosecant squared of u minus 1 du. Then we're going to say, sorry about that. Lost my train of thought for where I was going here. Okay, they messed up in the book. That's where I was heading. All right, so the antiderivative of cosecant squared is... Oops. Seriously? Come on here. All right, back on my train of thought here. The antiderivative of cosecant squared is cotangent, or negative cotangent, sorry, of u, minus the antiderivative of 1 is u, plus c. And so I get 1/3 of negative cotangent of 3x minus 3x plus c. And you can always distribute this 1/3 through. All right. Couldn't figure out how the book had a little integral symbol there, and it kind of threw me off. And make sure, those of you guys, you silly goofballs, do not multiply this 1/3 times this 3 inside the cotangent. It would be negative 1/3 cotangent of 3x. So I'd say negative, sorry, way down here on the bottom, negative 1/3 cotangent of 3x minus x plus c. All right, what about cosine of, or cosine cubed? Well, this one's going to take a little bit of work. So cosine cubed, I hope you guys understand that is actually cosine squared and cosine x. And cosine squared is 1 minus sine squared dx. So if I let u equal sine squared x, that means du, oops, sorry, not sine squared, just sine, my fault. If I let sine of, or u equals sine of x, that means du is equal to cosine of x dx. So I do substitution here. I say 1 minus u squared du. The integral of this, or the antiderivative, is going to be u minus u cubed over 3 plus c. And this one was actually pretty simple. This one ends up being sine of x plus sine cubed of x over 3 plus c. Final answer. All right. We can also, I think this is my last page, by the way. So what about definite integrals? Can we use substitution here? And the answer is yes. So if you get something ugly like this, tan x secant squared x, you can use your substitution here as well. You can say that u is equal to tangent of x. And you can say that du is equal to secant squared x dx. And this is actually pretty nice for this particular question because it ends up going from 0 to pi for u du. Now, there is something here that you do have to change up a little bit. And I'm sorry, this was supposed to be pi thirds. You can't actually use this thing anymore here for pi thirds. Or actually, you could, but if you would like to, you can actually change things around a little bit. If you wanted to know that, if you want to go at u of 0, tangent of 0 is 0, and then u of pi thirds is root 3. Instead of using any more substitution here, if I would have done this correctly, paid attention to myself, instead of going from 0 to pi thirds, I'm going to just stick with u and just say, okay, from 0 to root 3. So using new indices, I can say this is u squared over 2 from 0 to root 3. And this just becomes 3 halves minus 0, which is 3 halves. So this is the part that I forgot to mention as I was going here. When you set up substitution for a definite integral, you want to just change your indices in accordance to your u function. So take your u function, go from 0 to pi thirds, and you get 0 to root 3. So you can just change this from 0 to root 3 and do a very simple calculation. Didn't require much trigonometry at all. All right, so that's going to finish us off. Have fun with this. I will see you guys tomorrow.